Now we'll see one important technique called cache mapping technique. Okay, where we use and what is the motivation behind that we will see. Let's say you have small cache. Okay, we know that cache size will be smaller than main memory. So this is your main memory and this is your cache. Cache is having 4 blocks. So block size let us fix to 2 words. Okay, I am assuming that each block size 2 words. Now, so for time being, we assume that let's say our systems are word addressable. Okay, generally they are byte addressable most of the times, but we can imagine that our systems are word addressable. That means every word gets number. Okay, rather than every byte, every word gets number. Understand? Now, word size can be anything. Assume that let's say word size typically 4 bytes in our discussions. Word size I am fixing to 4 bytes. And every word is going to get a unique number, that means address. Understand? Now we will be dealing with main memory and cache, and we are understanding how to transfer the data from main memory to cache. Okay, so that's a story. Now, so here cache mapping technique is important. What is cache mapping technique is, whenever you want to keep data from main memory to cache, that is what we are going to do, right? Some of the data we will be keeping in cache, but example, let's say this is block number 1 in main memory, this is block 2, block 3, block 4, in that way there are 8 blocks and you have 4 blocks in the cache. Now block number 1 is having some data, right? Let us say D1. Now this D1 should go where in the cache? Generally, if and all if D1 wants to go here, then where it should go is the question. Then there are so many possibilities. One idea is direct mapping. These are all called cache mapping techniques. How you map D1? That means where D1 should go. That question's answer is mapping technique. It depends on the mapping technique. So there are 3 basically possible mapping techniques. One is direct mapping, second one associative mapping, third one is set associative mapping. Okay, you might think that, sir, we do one thing, wherever there is a free space, we'll keep the data there. Then what happens? Whenever you are searching in a cache, then because data can be anywhere, then probably you have to search all the locations, right? So that will take a lot of time, right? It will affect your the hit ratio of the cache. To avoid that, so we will be following a simpler model called direct mapping. In the direct mapping, what we do is, we will say like this: my dear main memory locations, like Mr. block number 1, let us use block number 1. My dear block number 1, you will go to only some specific locations in the cache. I will tell you what is that. Okay. Similarly, B2 also can go to only specific block. Okay. In that way, B1 can go to only a particular block. B2 also can go to only particular block. In that way, every block can go to only particular block. But according to pigeonhole principle, you have here 8 blocks. You have only 4 blocks here. Then, if you use uniform possibility, if you use uniform idea, that means then if you use any strategy, definitely at least each this kind of block will require to store at least 2 blocks, correct? You have only space for 1 block, but maybe you have 8 locations here, you have 4 locations here. The question number 1, how you keep this 8 in these 4 blocks? Impossible, right? Only at most 4 you can keep. Now the question is, then where you are going to keep B1? Let me ask. Let's here. Where B2? Here, let's say. See, one of the possibility. Where B3? Here. Where B4? Here. Okay, that is the way, let's say, you plan. Remember one thing, in direct mapping, we have to fix only one slot. Only in that slot we have to keep these particular slots. Okay, we have to map these 8 slots to 4 slots, and that's fixed. Example, let's say B1, we fix it to this B1, right? At any case, B1's data should go here only. B2's data should go here only. B3's data should go to here only. B4's data should go to here. Then problem comes. Then where you keep B5? For that, B5 should go to, let's say, again B1. Maybe if I plan like that, then there is a contention for this slot. This slot can occupy, I mean, this slot can only accommodate B1 or B5. Correct? Only one among them can be can be stored here. Remember that point. Okay, so that is a strategy called direct mapping. Finally, you have 8 blocks here, you have only 4 blocks. Then what we do is, in this model, every block always will be assigned a particular block in the cache. That means we map every main memory location, every main memory block to one particular block in the cache. Okay, we'll see more details of this direct mapping now. So how we can plan, I will tell you. Generally, how people plan this thing is like this. So this is again for simplicity, I take cache of size 4 blocks. Okay, 1, 2, 3, 4, and block size is, let's say, 2 words. Now let me imagine some main memory locations, exactly 16. Okay, let us take 16 locations. They are 0, 0, 0, 0. These are the memory addresses. Okay, for simplicity I am taking main memory of size 16. 16 words. Every word gets number, right? That's why 0, 1, 0, 0, 1, 0, 2, 0, 0, 1, 1, right? So then 0, 0, 0, 1, 0, 0, right? 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0. Then if I extend it, it will be 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay, let us show that 16 locations. This is your main memory. Right now, what I'm going to do is, because we are going to imagine this data as blocks, right? Because always we are going to transfer the data in blocks. That's why let us imagine these 16 locations into blocks. Then this would become block number 1. This would become block number 2, right? In that way. So now this would become block number 3. Okay. Now because every 2 words is one block. Block 4, block 5, block 6, block 7, right? This is block 8. There are 8 blocks. No. So what else we are going to do is, for mapping, we will be fixing, because see this, if you see the last bit 0, 1, 0, 1, they are really indicating the corresponding words, right? Here there are 2 words, word 1, word 2, word 3, word 4, word 5, word 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, right? Now see, the last digit, if you see 0, 1, why it is oscillating, you know, we can use it for the word number. That means see, in this particular block, word 0, word 1, word 0, word 1, otherwise word 1, word 2, doesn't matter, right? First word, second word, in that way. So I can say that whenever you have 16 locations, okay, 0, 0, 0, 0, this is the typical address. In that, this last digit is indicating the word offset, correct? Right, word offset. That means the particular word number, correct? If this block has 4 words, then we would have used 2 bits, because 2 bits are will get oscillated. Try to understand. Example, let's say for simplicity I'll show here. What if block size is 4 words? Then you see 4 words. What are the memory addresses of them? 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1. Then this 0, 0 part is fixed. This part will be variated, right? That means 0, 0 to 1, 1. So what I want to say is, when you have 4 words in a block, then these 2 bits will indicate that, right? If you have 2 to the power of k words in a block, then how many bits we have to take, so that, you know, which will represent that k bits from the left side. Remember that point. Okay, so k bits are required to differentiate them. Right here 2 bits are required to differentiate them. 0, 0 means one word, 0, 1 means another word, in that way 4 words, right? Now in our particular example, so this bit is really representing the word number, correct? Okay, 0, 1. So if you have any doubts, sir, why not last digit? See, last digit is not changing, then you can't differentiate using this bit the words, understand? So this is the right bit. Now the remaining bits, if you see 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, if you see these two 0, right? So this is 0, again 0, this is 0, 1, sorry, this is, I'm sorry, take 3 bits. Okay, let us take 0 0 0 0 0 0 0 1 0 0 1 0 0 0 1 1. If I remove this bit, first bit, then remaining 3 bits you see, okay, just try to convert it into binary, then it will become 0, sorry, convert it to decimal, 0, this, see this one, 0 0 1 1, see this one, 0 1 0, this block 2. Can I say one thing? This decimal equivalent of this binary pattern is just giving the block number, right? See, block 0. Let us number them like this so that it will be easy for you to understand. Let us number the blocks like this with 0. B0, B1, B2, B3, B4, B5, B6, B7, right? See, 0 0 0. These 3 bits are going to decide the block number. So that's why it is B0 block, right? 0 block. So 0 0 1, block number 1. 0, I mean, see the 3 bits right here. 0 1 0, block number 2. So 0 1 1, block number 3. 1 0 0, block number 4. In that way, last 3 bits can be used for block number. Now finally what we have realized is, in these 4 bits, these 3 bits we can use for block number. This bit is going to represent word number, right? Now we'll see another case, like example, let's say you have some 5 bits, 1 2 3 4 5. I'm talking about another case. So where you have, let's say, 5 bits, and assume that so each block has 4 words. In that case what happens? So how to split it? So that 5 bits will be divided into 2 parts. So these 3 and these 2, because we have 4 words in a block, 2 bits for that, and remaining 3 bits represents the block number. In that way, so block numbers and the corresponding words can be identified. Understand? Now, so we'll come to this mapping. Since it is direct mapping, so what happens is, so what we can do, I will tell you. Block 0, block 1, block 2, block 3, they will go directly to these 4 blocks. Block 5 again goes to in that block 0. In that way we can plan. You see, block 0 here, block 1 I can plan here, block 2 whenever I want to keep block number 2 of the main memory I keep here, block 3 here, block 4 in B0, block 5 in B1, block 6 in B2, block 7 in B3. In that way we plan it. This is called direct mapping. Now always B0 will go here itself. Always B4 will go here only. Now some students will have this question, sir, you have only 1 block capacity, right? How can you keep 2 blocks? At a time only we are keeping either block 0 or block 4, not both at a time, right? But if B0 is there here, then B4 will not be there. B4 is there, then B0 will not be there. That's it. Okay. Now let us focus on B0 and B4's binary patterns. Okay, B0's binary pattern, if you see, block number, these 3 bits represent block number, right? 0 0 0. So B4's block number, you see, 1 0 0, right? So this is B0, this is B4. Similarly, B1's block number 0 0 1, isn't it? Now B5's block number binary pattern 1 0 1, B1 B5. So we should have some strategy to easily map B0 and B4 to same block number 0, right? For that what we do is, see, we use these 2 digits, right? See, because they are not changing here. That's why I can see that whenever these 2 bits are zeros, then we can map to block number 0. Okay, this is block number 1, this is block number 2, block number 3. See, block 1, I mean B1, B5 of main memory, if you see this last 2 digits, they are same. That's why we are going to keep, we are going to map them to same location so that it will be easy. Why I am doing like that? It will be easy. Now this 0 1 indicates the block number of the cache. Now I got some shortcut. Example, let's say you want to know where B7 will be mapped, then take the binary pattern of B7. So we have 2 words, 1110, 1111, but we want to, we are interested in block number. This is a block number part in that 111. Then focus on that these 2 bits. What is that value? 3. Then definitely this block 7 is mapped to block number 3. In that way we can identify. So this is about direct mapping technique, and this is, whatever the procedure I told you, it is easiest way to map these blocks into these blocks. Understand? Now for B6 we'll see. Whenever you want to know where B6 is going, which cache block B6 is occupying, if you want to know what is the binary pattern of B6, I'm talking about only cache part, sorry, block part, not bit word part. Okay, so complete binary pattern, if you see for B6, it will be 1101 1110, correct? Sorry, 1100 and 1101, but I am interested only in 3 bits, correct? This is going to indicate the main memory block number. What is the main memory block number? 6. Where it will go, if you want to know, see this part. 10 means 2. So in that way easily we can say that B6 goes to B2. Now let us summarize whatever we did. Whatever the binary bits we have, 4, right? We divided it into 3 parts. So up to here, this is called word offset, right? We identified the word in a particular block. So this is your main memory address, right? 4 bits. Take a main memory address, split it into 4 parts. One is word offset. This second component is, sorry, split into 3 parts. Second component is cache index, right? Which I can say this cache index says that your main memory block is going to which cache block. That will be decided by cache index or cache offset. Now the third one is, usually said tag. I will explain the meaning of tag and why we use it. Okay, so this last digit is tag. Now let me ask one question. At this moment, let's say this is your cache. In this cache someone is there, but who is that? The only potential candidates are, already we know that either that potential candidate can be B0, otherwise B4. Now how do you know? It is just data, right? You are writing the data. Now if it is the data B0, what are the words in B0? D1, D2. Assume that the words in B0 are D1, D2. The words in B4 are D9, D10. Okay, D9, D10. Now similarly, let me write all the words. D1, D2, D3, D4, D5, D6, D7, D8, in that way. 9, 10, 11, 12, 13, 14. Let us take 15, 16, D15, D16. Now my question. Let's say somehow in this block number 0 of the cache someone is occupied. Who is that? One possibility, D1 and D2, 2 words, right? Otherwise the words might be B4's words. They are D9, D10. Now how do you know that at this moment it is set D9, D10, otherwise D1, D2? How do you decide that is the question, correct? So for that what we will be doing, I will tell you. So we will be adding the extra field called tag here. The tag is going to decide who is staying inside. How we will see? Example, let's say whenever you want to keep, example currently you store D1, D2 here, okay, one of the possibility. But you know that D1, D2 are part of block number 0, but your processor doesn't know, right? This is data, right? By seeing the data, can you say that data belongs to which block? No, right? So what we do is, example, what is for this D1, D2, what is the binary patterns, like what is your memory addresses? 0, 0, 0, 0, 0, 0, 0, 1, right? Now we ignore this part 0 and 1. Okay, so because that is only to differentiate the word offset, right? Now we are not we are not worrying about the corresponding word, we are worrying about this remaining bits 0, 0, 0. Now since these 2 bits are 0, 0, that's why we are keeping block number 0 here, fine. So in that way we use them. This 0 I write here, okay, if the data stored is D1, D2. If the data is stored is D9, D10, what I am going to do is I simply write D9, D10, okay, D9, D10 at that time. For D9, D10, if you see, the binary pattern is 1, 0, 0, 1, 0, 0, right? These 2 positions are again 0, 0, right? That's why this block is also going into B0. Now this tag bit will differ. Then I write here 1. From now onwards, if the tag bit is 1, that is block number 4. If the tag bit is 0, then that is block number 0. In that way, we can differentiate that to corresponding blocks. Now here also, there are 2 potential candidates, right? One of them will be present, but one candidate has tag bit 0 in the patterns. One candidate has tag bit 1. You can check anywhere, anything, right? That is the way these 2 are different. Example, you see, tell me 2 candidates who are going to same block. block number 2 and block number 5, I think, right? Now B2 and B5, because we know that B0 B4 one pair, B1 B5 another pair, B2 B6 third pair, correct? So B3 B7 the last pair. Now B2, what is the last three binary, what is the binary pattern for last 3 bits for B2? See, 0 1 0, word B6 1 1 0, right? See, 0 1 0 2, B6 1 1 0. Now that these two are same, that's why they are going to same, but this is different. So I do one thing, the tag bit I set appropriately so that we can differentiate among them, right? So that is the way this direct mapping will work. Now we will see the complete details because you understood the high level idea now. Now we'll see one clear example and we do the same so that you can remember the things. Okay, let us take a big example. Let us use, let's say, 16-bit memory address. Okay, assume that memory address is 16-bit main memory address, and number of cache blocks, let us use cache blocks as 1024. Okay, now each block has 16 words. Okay, now the question is here, how you divide your main memory. Now see, first step, how many each block has how many words? 16 words, right? That's why we divide, we give 4 bits for word offset. Fine. Second thing, so cache block size 1024, that means number of cache blocks here 1024, not cache block size, number of cache blocks are 1024. Then how many bits are required to differentiate them? 10 bits, correct? So the cache offset size will be 10 bits. Remember one thing, this number of cache blocks are going to decide these next 10 bits, right? Because we have to index into cache block. This is your cache with 1024 different blocks. So to differentiate them, so 10 bits are required. So what we will be doing is, these 10-bit pattern we will be using to decide which cache block we have to map this block. Understand? Now remaining things are said to be tagged, right? So in that way. So finally, word offset, cache index bits, right? Cache index bits, and third one tag, right? How to decide this I will tell you. Number of words, how many words are there in a block? 16, right? Then 16, to differentiate 16 binary patterns, then you require how many bits? Log 16 base 2, which is nothing but 4. That's why we use 4 bits here. Now after that, the next bits are going to decide the cache index, right? Cache index is decided by number of cache blocks. Did you remember in the previous example we had 4 blocks? So to differentiate 4 blocks, block 0, block 1, block 2, block 3, then we used 2 bits. Using the 2 bits we mapped our main memory blocks to one of them. These example, let us say take 2 bits, then patterns are 0 0 0 1 1 0 1 1. If it is 0 0, we send to block 0. If it is 0 1, we send to cache block 1 1 0, then cache block 2 1 1, cache block 3. That's why, so 4 patterns are enough to map our main memory blocks to cache blocks, because there are only 4 cache blocks. That's why 2 bits. So these 2 bits we are using generally. So that will become what? So cache index here in this problem 1024, then 10 bits, right? Log 1024, instead of 16 use 1024, so it would be 10. Total bits are 16, right? So 10 plus 4 14, then remaining 2 bits are going to be tagged, right? Now whenever you store the data, this is your cache, let's say, okay? In the cache, this is one of the block. So what we do is, this cache is going to have a tag field, okay? That means, so some extra memory where we can write tag pattern. So example, let's say you have one main memory block, okay? One main memory block. That main memory block, let us give binary pattern for that. So that 16 bits are like this: 0 1 0 1 0 1 0 1 0 1 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. The question, this memory address contains some word, right? Where it will go? Question number 1. Onto which cache block it will go is the question. If you want to know, then first divide it into 3 parts like this. Word offset 4 bits. So this is going to decide the word number in the main memory block. So now these 10 bits are going to decide the cache index. Take the 10 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Now remaining 2 are tag. So what are we going to do is, we will be taking 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So it will become one cache block number. So if you see the weightages, 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5, 2 power 6, 2 power 7, 2 power 8, 2 power 9. So 2 power 8 into 1, 256 plus, I am just finding the decimal value, 64 plus 16, then 4, right here, plus 1. It would become 256, 260, 320, 336, 340, 341, right? It would become 341. Let us check again. 256 plus 4, 270, 260, 260, 60, 320, 336, 340, 341. So 341 is the cache block number. Okay. So this main memory address word, which is going to 341th cache block, where cache block number starts from 0. Understand? Now if you really keep this data in that particular this is, let's say, 341 cache block, okay, cache block 341, then really if you keep the data here, okay, so whatever, I mean, data we get from memory, then this 0, 1 we keep here. That is what we do. Now while searching, how you do, we will see now. So far I explained you how generally data will be stored in cache, right, in direct mapping technique. So this is the way. Now we'll see how data will be retrieved, how to retrieve the data. Example, let's say this memory address, whenever it is referenced, then first we split it into 3 parts. Then directly we will take this one, okay, we take this one, and using that we are going to index into cache. I'll show that with one picture. Let's say this is your cache, okay, lot of blocks. How many blocks are there? 1024. Whenever a processor encounters a memory address like this 0, 1, let's see here itself. Whenever the processor sees this kind of memory address, this binary pattern will be extracted. Only this pattern will be taken. So using that, this cache will be, this is, let's say, cache. Okay, one thing, we can index the memory, right? So using this binary pattern, we will appropriately index into the right block. Let's say this is a right block, will come here. Then after that, immediately we check the tag. Why, sir? If tag is not 0, 1 here, then that means this data, the data at this memory is not really available in the cache, correct? Really cache contains the data, the tag should match. Sir, what if this tag is 10? That means 0, 1 doesn't match 10. That means data is not available in the cache. In that way, easily we can detect it. Understand? So at that time we say that cache is miss. If this is 0, 1, then 0, 1, 0, 1 matches. That means this memory address data is available in this block. Understand? So in that way we can easily check whether data is available or not. Okay, that is about direct mapping. Now we'll see the circuitry related to direct mapping. Actually, how this memory address will be properly analyzed, we will see. Okay, see the circuitry. So what happens is, whenever you reference any memory address, so your processor is going to first access the cache. First cache index bits will be taken. They will be connected to this cache. Okay. So finally, using this cache index bits, we will be properly indexing to the right block. Okay. At this moment, let's say if this is the right block, then first we know that there will be multiple candidates here, right? We don't know exactly whether our candidate is present or not. So for that, what we do, we check the tag field, correct? So go to tag field. The tag is connected to a comparator, and this tag will be compared. If tag bits match, then you get here 1 output. Then that 1 is connected to AND gate. So there is another input which is connected to AND gate, that is valid bit. What is valid bit? I will tell you. So initially you know, your cache blocks are absent actually, correct? That means, so initially when you switch on your computer, all these cache blocks are having wrong data, and that means no data, right? At that time, these valid bits will be initialized to zeros. Understand? Now, whenever data comes, then appropriately valid bit become 1. So, valid bit says whether the existing data is valid or not. Understand? Now, it will be confusing for you because, sir, whenever data is available, automatically valid bit is 1, right? So, if there is no data available, then valid bit is 0, right? Yes, that's it. But what is the purpose of valid bit if you want to see? There are two reasons. Initially, when you switch on your computer, so at that moment cache doesn't have anything, right? At that time, all that valid bits should show zeros. Okay, that is the way it will be initialized. Later, when some data comes to an appropriate block, then this valid bit will become 1. Sir, if that is the case, then why this valid bit we don't understand, because whenever data is available, then why this valid should become 1? Otherwise, what's the need of this valid bit? There is another reason for the need of valid bit. You see, sometimes what happens, we transfer the data from main memory to secondary memory. This is your main memory, this is your secondary memory. Assume that, let's say, so we are transferring data from secondary memory to main memory. That is also possible, right? These two different memory units. Now at that time, currently, let's say this is your data X, whatever it is. Okay. Now that X is already available in the cache also. So you know one thing, the same data whatever is there in main memory we kept in cache, correct? So there should be, for consistency purpose, this X and this X should be same, right? If this main memory content is modified, this also supposed to be modified, right? So assume that, let's say this secondary memory is, from the secondary memory we are transferring some data to main memory. Out of that, X is one word, okay? So maybe bulk, generally we do bulk transfers. Maybe you are transferring some 1000 words. Out of them, your word X is one of them. Then at that time, what happens, you see? Then this X will be modified. But already X is present in the cache, then that also should be modified. Understand? So that's why what generally people do is, whenever secondary memory modifies some of the locations of the cache in main memory, then valid bit of this cache will become 0, so that, you know, very quickly, so so that will be good, right? Otherwise, you know, it will show invalid data, right? To validate it correctly, so it should be 0. In that way, valid bit is used. Again, one more time telling example, you have some data here, let's say some word 1, but due to secondary memory transfer, secondary to main memory, the word 1 got modified. Then immediately this word 1 which is wrong should be invalidated. That's why we have to make it 0. So who will do that? Whenever secondary memory to main memory transfer is done, that is called, this transfer is called, you know, direct memory access. We will see that in IO. So this is direct memory access. So in this process, generally processor won't disturb this process. Generally we will see the details. It is unnecessary now. So whenever this kind of, you know, transfer happens, processor is automatically setting this valid bit to 0. Okay, that is the way we have to design our processor. Of course, for GATE exam that is not so important, but I would like to just share that detail. Okay. Now finally, you see only one, you know, comparison we are doing, because comparison takes a lot of time. Correct? Now slowly you understand the purpose of direct mapping. In the direct mapping, so your so-called word is going to occupy, if and all if it occupies, it is going to occupy only one particular position. Because of that, we are only directly, by using the cache index, we are directly going to the right place, and we will be checking whether data is correct or not. Understand? So that's why the direct mapping technique is fastest. But we will see the drawback. What is the drawback of this model is, example, let's say you some word is there already here, okay, some word 1, but what happened, you are referring word 2, okay, some word 2, let us write here word 2, but this word 1, this word 2 are different, but the relation between these two is they belongs to, if and all if word 2 is present in the cache, it's supposed to present here. Understand? That means what? These two are competitors. We have a block. In the block, either you can keep word 1 or word 2, not both at a time. because maybe this word 1 and word 2 belongs to two different blocks and of main memory, and they are supposed to be mapped to this cache block. Okay, now we will see clearly. This main memory contains lot of blocks, right? This is cache. In cache, let's say you have 4 blocks, okay, 0 1 2 3. In main memory you have 8 blocks, 0 1 2 3 4 5 6 7. Now currently in this cache 0 block, this 0th block is stored, okay, this entire 0th block. Now you know one thing, 4 also, if and all if you have to store 4, where you have to store? In here only, but now currently 0 is available. For some reasons, whenever you want to update this cache with 4, then 0 should be removed, correct? Now in direct map taking, that is a disadvantage. What is that? Though you have space here, you are not utilizing it. Rather than using it, unnecessarily you are just vacating 0, correct? So there is a serious contention, right? Now people are so rigid. This block 0, main memory block 0, main memory block 4 are so rigid. They want to go to only particular position. Of course, that method has advantage. Really, if they have that kind of attitude, then definitely what is the advantage? Then searching process will be easy. There is a trade-off, you see. Now always we will be searching only one particular location for one word, because we are keeping that word only in one particular block. Understand? But when you do that, so there is a lot of contention. There might be another word which wants to come here, but currently it is occupied by word 1, but there is a lot of space in other cache area, but you are not keeping it, because according to your formula that word also should come here. Then so definitely that is a drawback of direct mapping technique. So we have other alternatives for that. So that alternatives are associative mapping and set associative mapping. Associative and set associative.